Hi, today we will solve some examples on this important topic of gravitation, which is, as we said in the previous lecture, was the by far the weakest of the four types of interactions in nature. However, maybe the most important one in the macroscopic scale, because the other forces either are zero or very, very little, or since there is no net charge in neutral objects, such as electromagnetic interaction, do not act on the object. So the only remaining one in the macroscopic scale between objects, celestial objects, stars, planets, etc., or the other celestial objects, is the gravitation. The force, an always attractive force created by the objects because of the masses of their objects. Since an object has a mass, it creates its own gravitational field, as we will see soon. But now let's consider some examples on this important topic. Start with some relatively simple ones. Before solving an example, let me first say that it's a force. So force is a vector quantity. Therefore, directions are important. It has a magnitude, of course. Remember the formula. The force, the gravitational attraction was a certain universal constant of gravitation g times the masses of the two objects, because this is found by 2 by 2. Even if there are more than two objects, we find the resultant force by taking into account the mutual interactions. M1 with M2, M1 with M3, etc. So M1, M2 divided by distance between them squared. And since force is a vector quantity, we should take into account different contributions. If there are two or more than two objects in space, since force is a vector quantity, we should take into account different contributions. So in some cases they may cancel, in some cases they may reinforce each other. For example, if we have a one-dimensional system, let's say the x-axis, this is not an example, this is just a review at this stage. For example, if we have an object, let's say here, having mass m1, and an object here having another mass m2, and the distance between them, let's say, is L. For example, where should we put a third object having a mass m3 such that the net force on it is 0 and it can stay where we put it? For instance, Lagrange points are related with those positions. In free space, for instance, there are some critical points where, because of the equal and opposite forces acting on an object placed at that point, cancel, that third object, for instance, can stay there with almost no net force on it. And in this simple case, if this is the only picture we have, there are two objects, and where should we put a third object, M3, having mass M3, such that it can stay there forever? Of course, when you put, even before you put the third object, just these two masses, M1 and M2, apply a force on each other, obviously. So if you leave them for a long time, and in the absence of any other third object, maybe sooner or later they will try to get closer. Maybe they will hit each other after a certain time. This is known. And assume they are fixed. By some means, we fix these two objects in their places forever. And then we get a third object from somewhere, and we want to put it somewhere here, such that it can stay wherever we put it. It is obvious is that from symmetry, for instance, we cannot put the third object anywhere in the upper part or anywhere in the lower part of the x-axis. What is x-axis? It is the axis that joins these two objects in free space. So the only possibilities are necessarily, first of all, are the points on the axis. Otherwise, it is impossible to keep this third object in equilibrium. Now we have three choices, maybe to the left of one of them, or to the right of the other one, or somewhere in between. If this system were an electrical system, and these objects were electrical charges, Q1 and Q2, then we would be interested in the signs also. Are they positive and positive, negative and negative, positive and negative? However, now we don't have any such interest, because in the unlike the electrical case where we can have attraction or repulsion, depending on the signs, here we have necessarily only attractive forces. So whenever we put the third object, these two bodies will exert attractive forces on the third. So if you choose first region, domain 1, and put it somewhere here, this object will try to pull it, attract it. This also will try to pull it also from a greater distance, but it will apply a force. So these two forces are both in the positive x-axis, they don't cancel, so it is impossible to choose region 1. Similarly, region 2, because if you put the third object somewhere here, both of them will apply forces in the same sense, so there is no possibility of cancelling. The only possibility is the region 3, somewhere in between. And the next step is to find exactly at which position we should put it. And it is that easy, we can get from even from high school information. We choose a certain position, let it be, for instance, x, unknown x. Of course, the rest will be L minus x, and by just writing, equating the forces, for instance, on the force on this object, now we can erase the rest. So we have this line joining them. The distance is L. This total distance is known as L. And assume we choose such an unknown position, and let this part be x. Of course, the remaining part will be L minus x, so that this object M1 will try to pull it to the left, but M2 will do it in the opposite sense. And if they exactly cancel each other, M3 will stay at rest forever. So this leftward force will be capital G, M1 and M3 divided by x squared, and the other one is G. This time we have the other object M2 and the third object M3 divided by L minus x squared. If we cancel these G's and M3's, we have a certain ratio. That ratio is M1 over x squared, M2 over L minus x squared. If you know M1, M2, L, it is easy to get the unknown x, because if you take the squares of roots of both sides, this will be root M1 by x, root M2 by L minus x. So by arranging the rest, you can get, for instance, x over L minus x will be root M1 over M2. And after just the equation, etc., you can find the exact position. Let me just complete it. X times root M2 on the one hand, L minus x times root M1 on the other hand. So x multiplied by, take it to the left, root M1 plus root M2. Remember, it is not root M1 plus M2. It is root M1 plus root M2. Unfortunately, there are some people who can make such mistakes. So let's on the right hand side write L times root M1. Therefore, x is easily found to be root M1 by sum of the roots M1 and M2 multiplied by the length L. Of course, this fraction is less than 1, that ratio. If you, by mistake, if you find a fraction, if you make some mistake, if we make some mistake, during these calculations and get, for instance, something, if this fraction is greater than 1, it is obvious that what the position will be is somewhere outside this L. It is already eliminated. We have eliminated these choices 1 and 2. So this fraction should necessarily be, first of all, unitless. Yes, mass per mass, unitless, all right. And then necessarily should be less than 1, so that x turns out to be less than 1, less than L. And this is even not an example, it's a very simple review. Let's continue to do some other points in the review part and then solve the first example. For instance, since it's a force is a vector quantity, of course we are interested in the directions, and directions are represented by unit vectors I, j, k, or e1, e2, e3 if you use a maybe a bit more scientific notation. e1, e2, e3 the unit vectors along the x, y, z axis, etc. But now let's consider let me just write the first steps and don't continue. So let's say we have 3 objects, mass m1, m2, and m3. And these distances are, let them be a and b, for instance. A and b. And we will simply write the net force, resultant force on m1. Resultant force. If you want to find the resultant force on m1 due to the other masses m2 and m3, of course in vector notation. It is quite easy to write such forces because now let's focus on m1. Of course m1 does the same on the other objects, but we are not interested in what m1 does. We are interested in what the others do on m1. So there is a force due to m2, there is a force to the right, let me call it F12. It is not F12, it is F12. Force on 1 due to 2. Next one is this force, which is, let me call it F13. Force on 1 due to 3. And it is quite easy to write those forces because F12, this one will be capital G, mass of the first one, mass of the other one that applies the force, divided by this distance squared. And similarly, F13 will be similarly m1, m3, g times m1, m3 divided by b squared. But if you want to write this in vector notation, the resultant force, we should use I and j. So the resultant force will be F on 1 as a vector with a single index. G is the common term, M1 is the common term, multiplied by M2 over A squared, M2 over A squared times the unit vector I, because it is pointing to the right, plus M3 over B squared unit vector J, because it is pointing in the positive y direction. So this is the resultant force on M1 in unit vector notation. Conversely, for instance, if you wanted to find the net force on M2, for instance, I will not continue, but let me just write the first step. Instead of this, for instance, if we wanted to find the net force on M2, then M1 would apply a force to the left. Of course, its name would be F21 because this is the force on 2 due to 1. And a bit more geometrically, a bit more complex one is the other force because this object would apply a force in this direction. It is called F23 because it is the force on 2 due to 3. Let me just write these in the first step and then pass to the first example. What is this F21? Of course, F21 is the same as F12 in magnitude, but directionally they are opposite vectors. So what is that F12? Whatever we write here, G times M1, M2 by A squared. But if you want to write it in vector notation, this is just the magnitude. If you want to write it in vector notation, it would be F21 with a vector. Since it points to the left in the minus x direction, we would write minus G M1 M2 over A squared multiplied by unit vector I. Because it is now in the negative x axis, this would be only one force, F21. But F23 has two components, obviously. One is in the horizontal axis, the other is in the vertical axis. Horizontal one is, now this angle is required, but it is not given. Although it is not given, we can write it using these sides A and B. A and B help us to get the sine theta, cos theta, of course. So let me write just the components of F23. F23, just the diagonal one. Hypotenuse. What is it? G times two masses, M2, M3, divided by which distance? From Pythagorean theorem, we have squared plus B squared. That's it. However, let me write them separately. F23 x component, F23 y component. In this case, it is F23. If this angle is theta, cosine theta. The other is F23 sine theta. But what are cosine and sine theta? Using the size of the right triangle, we can get the expression in terms of given parameters. So let me write F23 x component, of course, G M2 M3 divided by A squared plus B squared multiplied by cosine theta. What is cosine theta? It is A over root of this quantity. It is A over root of that A squared plus B squared. Here, similarly, in the other case, for the vertical component, it is G M2 M3 divided by A squared plus B squared, but now multiplied by opposite side over the hypotenuse, which is B over, again, the same root. So let me write the final results here and then go to the other example. F23 x component is, or in general, F23, for instance, F23, not just x component. Let me write it in the vector notation. It is, first of all, G, M2, M3 are common terms. Let me write G, M2, M3 outside. G times the masses multiplied by, what is remaining here? We have A over this term to the power of 3 halves. Even we can write it here outside, A squared plus B squared to the power of 3 halves. This power of 3 halves will appear later again in other problems. This is the common term multiplied by, what is this inside? A times unit vector I, but it acts to the left, so we have a minus sign. and for the other term, plus because it points upward, b over b times j. That's it. So this is the force on the object mass 2 due to mass 3. However, there is also this part, F21, because of the other object, so that this term, first one, is added to this one. However, this is the only one in the y direction. So now let's consider the next example. Let me write it. Let's first draw the picture and then write the text. The picture is the following. Here we have an XY system, origin. But we put two identical objects symmetrically on the two sides of the y-axis. These masses are capital M, capital M. Two identical objects of mass m are placed symmetrically at x equals minus a, so this part is a, and x equals plus a. Where should we put a third object of mass little m, a third object of mass little m, such that the net force on it such that the net force on it is A minimum, B maximum. Of course, we may remember from this example from electricity, for instance. Because in electricity, we have a similar problem. What is that similar problem? We put two charges here, identical charges, plus Q, for instance. And we have a third object having a different charge, but no, that doesn't matter. Where should we put the third charge, Q prime, for instance, along the y-axis? Of course, it is obvious that along the y-axis we are interested in the perpendicular direction and midway, A and A, midway, such that the force on this third charge is zero, or maybe zero, maybe minimum, and also, maybe more importantly, where should we put it such that the net force on it is maximum? And this is just the same idea. So if you understand this one, we will easily solve the counterpart in electricity, of course. Now let's draw lines between masses. For instance, let's join, for example, let's say we have chosen this distance. So this distance from the origin is y. And the object of little m, mass little m, is put here. We don't know this y. We will find the possibilities. And join the other mass also. So these two forces, these two masses will apply forces. And since they are attractive, this will be, let me put just F. This is also equal, but in that direction. What is this angle? That is P theta. symmetrically placed, these two forces have equal and opposite x components, but y components that can add up. Let me draw the picture again, this part. So these are the forces, and this one fx, that one fx, and they cancel each other because of symmetry. But vertically, they have to be added. These are fy and fy. What is f first of all? F is equal to one of the forces f is just g times the masses divided by the distance squared. G, capital M, little m divided by this distance. What is it? One part is a, the other part is y. Although unknown, we name it as y. So it is simply a squared plus y squared. No need to take the root, it is just a square. But fy, fx components cancel. Fx components cancel, fy components add up. So that we write fy is simply f times cos theta. But what is cos theta? We don't have angle theta, but we have y over hypotenuse. It is f times y over root of a squared plus y squared. So we have the same term, one just itself, the other in square root. Therefore, this fy will be, we should first of all multiply by 2, f total, let me call it f total y. Because there are two such forces, we should multiply by 2. 2 times g capital M little m divided by a squared plus y squared to the power of 3 halves. So this is the expression for the y component. When do we have, there's a y here. Now this is the result. But we want to find the values of y at which that force is minimum or maximum. Minimum is easier. Just by looking at it, you can understand what it should be. First of all, if you set y is equal to 0 immediately in the numerator, which means we should choose just the origin. If y is 0, we have the origin. Of course, at the origin, when we put the third object here, these forces are equal and opposite, they cancel, and we have minimum force. So y is equal to is a possibility, but not just the only possibility. At y is equal to 0, it is a minimum force. No force, 0. But there is one more, there are two more possibilities. If you look at the denominator, it is something plus the unknown y squared. If you choose infinitely high values for y, which means you put your object, third object, very far away in the positive infinitely high values of y, or negative infinite downward, very, very far away positions, then the effects of these two forces are negligible, so they can be considered as 0. But one may consider that if you put infinity in the denominator, we should put, if you put infinity here, infinity squared, we should put infinity here. Do they cancel? No, not exactly, because this is something squared. These squares will cancel, so we have some y to the power of, this is negligible, y to the 3. This is just y. Y over y to the 3 means 1 over infinity, which is also 0. So the minimum part is easily seen that there are three possibilities. One, to put the third object just at the origin, where y is 0, so that the numerator is 0 and force is nothing. The other possibilities are symmetry cases, plus infinity. Now part B requires some more attention. It is not easily seen from this result in part A, because we want to find the maximum value. How can we find the maxima, minima in such cases? Maximum values, minimum values, optimum values, optima, etc. or inflection point in some cases. We don't have inflection point in such cases, but minimum is also found. But what about the maximum possibilities? Of course, if you want to maximize a quantity, such as the force, by changing a quantity that we can change, the variable such as this y, because we can play with only the y value. By changing the masses, if you put a larger mass, capital M, of course you get larger force, but it is not the question. If you put some other 2m here, 2m and 2m, of course the force will be greater, but we are not interested in that. We are interested in the position y with the given data. Given data are capital M are the mass, distances are a and a. Even the third object, little m, is not important because we are interested in the force. This force, if you want to maximize it by changing, playing with this variable y, has to be maximum. So we have to take the derivative of force. We have to differentiate this quantity that we have to maximize with respect to the variable that we can change and set immediately that derivative to 0 and find the possible solutions. So in this case we have to take in part B, we have to maximize, or we can maximize the force by just taking the derivative of f with respect to y. You can maximize or minimize, of course, but in this case, minimum values are already found. We can maximize f by taking the derivative del f by del y, partial derivative in general. However, here there is only one variable, so we can write it as a normal derivative df or df by dy. We can, by taking the derivative del f by del y and setting it to 0. So that we take df by dy and set that ratio to 0. And f is this. df means the del fy, we consider y component, of course. Anyway, there is no x component, it is the y component. So if you take this derivative and set to 0, we will get it. We have some constants, 2g and m. So we have, let's say, 2g and m. Not important, they are already constant. Multiplied by, let me write it totally here. df by dy, 2gmm multiplied by, since it's a ratio, remember that derivative f over g, derivative will be f prime g minus g prime f divided by g squared in general. If you have a fraction, numerator over denominator, derivative of the upper part times the denominator minus derivative of the denominator times the numerator. And this is not important, of course, because we will set this is up to 0 anyway, so the numerator should be 0. Let's continue here. After this constant part, we have derivative of the numerator, which is 1, and the denominator totally. A squared plus y squared to the power of 3 halves. Minus derivative of the denominator, which is 3 halves, times the inside, to the power of 1 less, 1.5, 1 less is 0.5, which is 1 half. But don't forget to write derivative of the inside coming from the inner part, which is 2y. 2y, and altogether divided by something which doesn't concern us. So totally this has to be equal to 0. Forget about this part, not important. These 2's cancel, This part is not important. So we have on the left a squared plus y squared to the power of 3/2 only. On the right we have, take it as a positive term, 3 times a squared plus y squared to the power of 1/2 times this y. Take it to the other side, they are similar terms. So a squared, etc. This part, a squared plus y squared to the power of 3/2 over the same term to the 1/2. On the right, we only have, and also there's a y here coming from the f. G prime is that, but f is missing, so there's another f here, y squared. So we have 3 times y squared. So after the cancellation, we have just a squared plus y squared to the power of 1 turns out to be 3y squared, and finally y squared is a squared over 2. So y is equal to plus or minus, don't neglect the negative possibility, plus or minus a over root 2. So these are the places where the force will be maximum. So y is equal to a over root 2. What is root 2? 1.4. So a over 1 over 1.4. This is the initial case. These distances are a and a. Just a single a corresponds to somewhere here. It is a bit less than maybe here. These are the positions where the force will be maximum. So let's consider this as a whole. If you have this object, these objects as given by the figure in the problem, so these are the identical masses. And you take a third object, maybe little, maybe more. It doesn't have to be less than the capital M. It can be greater because we are interested in the net force applied on it. So if you start with y equals 0, if you start from the origin, there is no force because the two are cancelling. If you continue to move here, force is getting greater because between 0 and this value is somewhere here. Let me call it a over root 2 is somewhere here. It is less than a. More than half, 5 over 7. So nearly 70%. So this is nearly 70% of A. This is just A and A. So 70%, 0.7A approximately corresponds to here. Between 0 and this critical position, force on the third object is increasing. But after that, decreasing. So in this part, F increases, but from then on, F decreases. Okay? So if you plot, for instance, this is the y-axis, for example, and if you want to plot the force Fy, force, we talk about the vertical component because there is no horizontal one. This vertical component, until we arrive at the critical, starting from 0, until we arrive at the critical value of a over root 2, force is increasing, but we don't know how it does. We can find it, but to draw it exactly is not easy. Maybe by looking at the formula. What was the formula? F was something, constant terms, 2g, mm, etc., multiplied by y over this plus y squared to some power of 3/2, etc. So that force is increasing this way. We are not interested in the intermediate parts. Here it arrives the maximum position, so that we have found this value for the maximum force, and then it is decreasing and getting zero as you go away. So this is the critical position, both for the masses and for the electrical charges. As I said before, if you put two identical charges here, you would get the same behavior for the force or for the electric field, of course, or the gravitational field. We didn't talk about the field yet, but the gravitational field created by every object having a mass, or every charge, every object having an electrical charge, they create fields. The concept of field I will try to talk about later. So the field is also increasing first from the origin until you arrive at this maximum critical position here, and then this behavior in between can also be found, drawn by choosing certain values in steps. But we know that it starts from zero, it arrives at the maximum here, the critical point. So this is a downward curve, the downward looking curve, concave down, and then necessarily it decreases afterward and reaches zero again, like the origin. Again it reaches the plus and minus infinity. Later on we will see Kepler's laws when we have the celestial bodies, solar system for instance, etc. But now even we don't need such three laws at this stage. We can solve even some problems without knowing about the Kepler's laws. Let's consider some satellite around the Earth, or planets around the sun, or an artificial satellite, or the natural satellite, the moon, etc., turning around a central object having a certain mass. Let's consider some examples for that. For instance, in this case, let me first write some piece of information. If an object such as a satellite, maybe a TV satellite or communication satellite, or just our natural satellite, the moon, this idea is the same. If an object such as a communication satellite, for instance, is turning, let's say, off mass, but the mass is not important unless it is comparable with the mass of the central object. If we assume that the mass of the satellite, even the moon, has a mass much less than that of the Earth, if you talk about the TV satellite, of course, it is on the order of some kilograms. Compared with the mass of the Earth, it is totally negligible. If an object such as a satellite of mass m, anyway this will cancel at the end, is turning around a center, such as Earth, then the centripetal acceleration it has to have is supplied by the gravitational attraction. Then the centripetal acceleration, let's say A, is provided by the gravitational attraction of the Earth. Is supplied by the gravitational attraction of the Earth. So this is the main idea, and it is not difficult to see it. Because if something, as I said before in the previous lectures, if let's say we have a central object or no central object, if we have a car moving in a circular track. Of course, this turning object, whatever it is, should have an acceleration inward, of course. There is nothing outward. I will talk about it when we come to the other chapter in non-uniform frames. We will have such, we have more about this to say. But here we say that the acceleration, let me call it centripetal acceleration, wherever it is, and this is not a this is a horizontal circle, by the way. We have a car, for instance. This car is moving and turning in a circular way on a horizontal surface, so this is the top view. It should necessarily have an acceleration towards the center, so that it can change direction, because the velocity vector is continuously turning. That turning is supplied by this acceleration, even though the velocity, the value, the speed is not changing. Alright, we know this much. So this acceleration, centripetal acceleration, is supplied by the, in the case of the car turning in a circle, is supplied by the friction force between the tires and the road. In the case of, for instance, if something is turning, by, for instance, we have, let's say, if you have a rope attached to a rope, an object, this object is turning in a conical way, for instance, then it is the tension, the x component of the tension that supplies the necessary acceleration, centripetal acceleration. In the case of some, let's say, charges, for instance, some particles are turning in an accelerator, for example, and that acceleration in sand, for instance, some particles, protons, antiprotons, are continuously turned around in a circular way, and those particles they have some centripetal acceleration. It is supplied by some QVB type of force, etc. And in this case, we have none of them. No friction in the satellite Earth system or Earth-Moon system. There is no tension, no rope in between. No friction in between, no QVB type of charge, velocity, magnetic field. There is no magnetic field in free space. So that the only force that can supply this acceleration is the gravitational acceleration. This is obvious. So in the example, let me indicate this point again. By the way, in astrophysics, there are several different types of objects, of course, stars, but different types of stars. For example, we are not now interested in the physical processes that take part in those periods, but sometimes, under some conditions, some circumstances, a star sooner or later becomes a neutron star. A very large density, not as dense as a black hole, but quite a large density. For example, if the total mass of the Earth is compressed down to like a region of a city, for instance, then it is still visible. It is not a black hole yet. However, the density is quite high. Maybe 1 cubic centimeter of that matter has a mass of maybe 10 to the 5, 10 to the 6 kilograms, etc., maybe more. Let's say now such an example, but not in the point of view of the physical processes that occur, but just indicating this idea, how it revolves so that it creates such an acceleration on the surface. A neutron star, which is a very dense object, is observed to rotate around itself at an angular velocity of 1 revolution per second. A neutron star is observed to rotate around itself with an angular velocity of let's say 1 revolution per second. If the radius, of course, we say the radius is quite small, it is on the order of some tens or hundreds of kilometers, maybe less, but a huge mass. If the radius is just, let's say, 20 kilometers, what should be the mass at least lower limit? Because it can have upper limit as well. If there is no upper limit, it can have only lower limit. If it is even denser than that, there is no harm for the objects on the surface. They can still be attracted towards the center of the star. But it should necessarily have a certain lower limit for the mass, such that an object on the surface keeps rotating with the star and not leaving it. Okay? If the radius is just 20 kilometers, what should be the lower limit for its mass, m, capital M, for instance? What should be the lower limit, minimum value for its mass m, such that the objects on its surface keep turning with it. Well, the same idea applies. Here is the star, neutron star, for instance, very dense object, and let me draw it as a circle. This is a very dense object, all right, but it has a certain radius and is turning at a certain omega. That omega is 1 revolution per second. The whole star is turning every second, once every second. So that omega is given, radius is given. So what is the physical idea? If you have a mass here, any object, this should have an acceleration, centripetal acceleration towards the center. That acceleration, what is it? For instance, gravitational force is G M is capital M is the mass of the star, little m is the mass of the object, whatever that object is. Assume it can withstand the high temperature, for instance, on the surface. Of course, it is not easy, but assume a particle having enough strength to withstand the high temperature on the surface. That object, if it keeps rotating with the sun without any shifting on the surface, should have an acceleration, centripetal acceleration towards the center by this gravitational pull. That should be equal to mv squared over r. Remember from the physics 101 we know mv squared over r. But this is not v yet, it is omega. And we know how to relate v and omega because v, linear speed, is angular speed times radius. So that we have, after we cancel the mass of the little object, so we have capital G, capital M divided by r squared equaling m cancelled. V squared is now omega squared r squared divided by r, so this is equal to omega squared r. And you want to find this mass. And we know omega. What is omega? 1 revolution per second. But revolution per second is not an SI unit. Instead, we should use radian per second. Omega equals 1 revolution per second. It is just 2 pi radians per second. So if you put this omega here and g, we can easily get the necessary lower limit. So for instance, capital M here is just r cubed omega squared r cubed divided by g. Now let's put the numerical data. Omega is 2 pi squared. Radius is 20 kilometers, so it is 20 times 10 to the 3 meters to the power of 3 divided by g, which is 6.6 10 to the minus 11. Now the result will give us the limit for mass. So it is 4 pi squared. 4 pi squared, it will be 2 times 10 to the 4. 2 cubed will be 8. 10 to the 4 will be 10 to the 12. 10 to the 4 to the 3 times 10 to the 12 divided by 6.6. And let me take this upward as plus 11. There are some cancellations. For instance, pi squared is 10. Remember, it's a practical substitution. Pi squared is generally taken to be 10. So that there is one more power of 10. Let me take it as plus 1. But 4 times 8 is 32. Divided by this is almost 5. Almost 5. Not very important. 5 times what? 12, 20, 24. 5 times 10 to the 4. So that mass lower limit should be at least 5 times 10 to the 4 kilograms. If you remember the mass of the Earth, mass of our Earth is just approximately 6 times 10 to the 4 kilograms. It's quite comparable. For example, roughly 80%, an object having almost 80% of the mass of the Earth should be compressed to a radius of just 20 kilometers. In that case, that new sphere, which is very, very dense, is now has become a neutron star. And it rotates, for example, around its own axis at a rate of 1 revolution per second. Very high rate of revolution. So far we have seen that gravitation occurs between objects having a certain mass, but we assumed it to be concentrated at the center, for example, between two spheres or two compact objects. However, we may have some extended objects as well, so we may want to investigate the effects of the gravitational effects of some extended objects, such as a rod, for instance, or a surface disk. Let's now consider a certain rod having a certain mass and a length, and find the force on an object which is placed along the intersection but bisector of the rod. A rod of length 2a, it is symmetrically placed across the hypothetical x-axis. We put our hypothetical x-axis along the bisector of this rod, so that the length of the upper part and the lower part are both a. A rod of length 2a and mass m mass capital M is placed, let's say, across along the y-axis. Is placed along the y-axis. Find the gravitational force on an object of mass little m placed at a distance b from the midpoint of the rod. At a distance b perpendicularly from the center, from the midpoint. From the midpoint of the rod. So in such cases, we don't have a single object. Yeah, we have a single object as a rod, but we have to take it piecewise. So we consider the rod as composed of several mass elements along its length, and we will find just the effect of one single such small piece, infinitesimally small mass element dm, and by adding up, which means by integrating all these contributions, we can get the final full resultant force on the little object. So let me draw choose these mass elements. Here, for instance, let's draw the picture again. So this is the rod. And here is the little object, little m. So we take a small piece. We know the full length, A, alright, but we are interested in a very small mass element dm, any such mass element dm, d capital M, at a distance y, for instance. So this distance, let's say, is y. But the other length is fixed. It is called b. So this is the distance b, horizontally, and only this small mass element dm, of course we have to choose the symmetrically opposite one. If this is dm, this is also dm, and the distance of the symmetric point particle is also y from the midpoint. So what is the force exerted by just this single, simple dm? Here we have a small vector. That small vector is df. And this one does the same at the same angle, and this time in the upper part of the x-axis. So this is also df. So these df's for any pair of particles cancel in y direction but add up in x direction. As you see, they have vertical, horizontal components which cancel, but horizontal components which add up, dfx. Again, let me write the usual sentence. dfy's cancel, dfx's add up. So dfy, dfy. dfy components cancel, dfx components add up. This is the main idea. What is just a single df? Just a single force element df without any component. This df, just the resultant one, is written as df is of course the famous constant of universal gravitation, capital G. This mass element dm, the other mass, which is little m, divided by distance between them squared. What is that distance? It is that distance. Let me now call it r. The distance is r squared. What is r squared? where r squared is just from this right triangle, y squared plus b squared. B is constant, y is variable. Next, df(x), which we are interested in, is now this df multiplied by, let's call this angle, that angle, all of them, theta, 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 and theta. Df times cosine theta. But since theta is something we invented, we should convert it, we should express it in terms of given parameters. What are they? B, y, for this ordinary triangle, df cos theta, but cosine theta can be written as, for this angle, the adjacent side divided by the hypotenuse. The adjacent side is just b divided by r. So that df(x) component will be total df this much, g d capital M little m divided by r squared multiplied by cos theta, which is b over r. If you write r in terms of the given parameter b, it will be capital G dm times m times b divided by y squared plus b squared to the power of 3/2. Because r cubed, r is the root of that, its cube will be to the power of 3/2. Now the next event is just to add up. Since we should add up all such components, totally f in the x direction will be sum over all the fx elements, which are some of them. And what about the limits? Once we write the right hand side, we consider the limits of variable, which is limits of y. So this is just, let's take the constants out, g little m b divided by nothing yet. These are the constants we can take out. Inside the integral we have dm. Well, what is dm? It is this small mass element. But dm can be written as, d capital M can be written as linear mass density lambda times the small length dy. Because if you consider this piece here, this piece, this length is just dy, because we talk about the y direction. And the mass just in this part is dm. If you multiply the ratio of the mass per unit length, which is a general information because it's assumed to be a uniform rod, then this dm is just the product of its linear, just like linear charge density. We have a rod, for instance, charge rod. Total charge Q is distributed along a rod of length L. What is the linear charge density? It is Q over L. We don't have charges now, we have mass. So the linear mass density is, by the same idea, total mass, which is capital M, divided by total length, which is 2a. But we can now consider it as lambda at the end, we can replace it by the right hand side. So inside we have lambda times dy divided by this denominator, y squared plus b squared to the power of 3/2. Let's consider the previous terms as g and b lambda. Let us call this part capital A for the time being. Inside we have dy divided by this term to the power of 3/2. How do we solve this integral? It is not difficult because there are some ways to calculate this type of integration. One of them is just trigonometric substitution by applying trigonometric substitution. But what should be the correct choice? Is it a sine theta, cos theta, tangent or cotangent, whatever? Trigonometric substitution. Remember that we know from previous experiences, if we have a subtraction in the denominator, it is better to substitute sine theta or cosine theta instead of y. For example, if it were, if for instance we have something, let's say 1 over b squared minus y squared, then it would be better to use y is equal to b times sine theta or b times cosine theta, because in one of these cases it would be b squared minus b squared sine squared, so that 1 minus sine squared. What is it? Cosine squared theta. Or applying the second choice, again we get the same 1 minus cosine squared theta is sine squared theta. Because here we have, for instance, dy in the numerator. If you choose the upper choice, then dy will be b cos theta d theta. If you choose the lower one, then it is minus b sine theta d theta. So that there will be cancellations and you get the result more easily. However, now we don't have a subtraction, we have an addition. If you have an addition of two squares, one being a constant, the other being a variable, the best choice is to use tangent theta. Anyway, if you look at the picture here, this graph, we have a triangle like this. What about tangent theta in this triangle? It is y over b. So if you choose, use tangent theta is equal to y over b. So the choice seems to be y is equal to b times tangent theta. So this has to be our choice. Next, once we have chosen this substitution, what happens to dy? Let y be b tangent theta. Then, of course, we have to use the dy because we have dy in the numerator. What is dy according to this choice? Dy, the derivative, differential on the left hand side, is the differential on the right hand side. What is it? B is a constant. Tangent, once it is differentiated, becomes secant squared theta. Don't forget this d theta, otherwise it is missing. So put this dy in the numerator. And in the denominator, put this choice. Therefore, fx will be this constant a, write it as a now. In the integral, we have dy. What is it? b times secant square theta d theta divided by. And we have something to the power of 3/2. What is this parentheses? Y squared. It is b tangent theta squared. B squared tangent square theta plus b squared to the power of 3/2. We can take out a and b from the numerator. Inside we have secant square theta d theta. Here we have b squared, because this parenthesis becomes b squared and tangent square theta plus 1. But tangent square plus 1 is just, remember, secant square theta. But don't forget to take these powers, raise them to the power of 3/2. So for the b squared term, these two cancel, we have b cubed. We take it out, b cubed. For the other term, this 2 and that 2 cancel, so we have divided by secant cube theta. And we have a single cancellation, so it becomes b squared. Next, secant squared cancels two of them, and we have 1 over secant inside the integral. So it will be a divided by b squared outside. Inside we have only d theta by secant theta. But secant theta by definition is just the inverse of cosine theta. So 1 over cosine becomes cosine. So secant theta is just inverse of cos theta. Cosecant is the inverse of sine theta. So that it is 1 over cos, it becomes just cos. So that we have a over b squared integral cosine theta d theta. And we know how to take this simple integral. Cos theta d theta is simply sine plus sine theta, not minus sine like the derivative. In the integral we have plus sine theta. So at the new step we have a over b squared outside, and it will be just sine theta. But sine theta or anything, tangent theta, is something we have written. So we should go back before this step and look at this triangle. In this triangle, alright, this was the angle theta, that was the side y, and this was y squared plus b squared. Sine theta in this triangle that we have been using is just, sine theta is y over root of, now it is the square root of y squared plus b squared. Let's continue to the final step. Then what happens here? We have f in the x direction is a over b squared multiplied by, we don't write sine theta now anymore, we use the right hand side. It is y over y squared plus b squared, and the limits are y is equal to 0 is the midpoint, ranges up to a. So y is equal to 0 up to y is equal to a, but don't forget to multiply by 2 because there is just 1/2 for this range. We should have one more. Once you write this, you should multiply by 2 to take into account the lower part as well. So now let's replace a with the previous a. What was it? Fx is just 2 over b squared. A was just capital G, capital M, and lambda that we have taken outside before this simplification. And inside the parentheses, we have written 2a to gm lambda divided by b squared. Inside we have, if you put a over a squared plus b squared. If you put 0, you get 0. So there's no second part. And lambda is, remember, lambda is equal to total mass by total length, which is m over 2a. And finally, we have gm. Instead, don't forget this b squared. For lambda, we write m over 2a. Here we have a over a squared plus b squared. So these 2's will cancel, those a's will cancel, and we obtain at the end the net force Fx, of course, f in the x direction, is just capital G, capital M, little m, divided by b squared multiplied by, there was a b also here. For this case we had a b, so one of the b's should cancel. So there's no square here, otherwise the units do not match. So there was a b in this a, there was g, m, lambda, and also a b together, so don't forget it please. Therefore there is only one single b in the denominator, otherwise in the denominator we will have not distance squared but distance cubed, which is meaningless. So here we have a squared plus b squared. And let me write a comment, immediate comment. For much larger distances away from the rod, what do we expect? Comment. For very far away positions, for very far away positions. Far away positions means B is much, much greater than the dimension, size of the object, 2A or 3A, 1A. So B should be much, much greater than A. What happens to this result? If you neglect the smallest one, the smaller one of these two, if you neglect this A squared, because if A is much less than B, if A is much less than B, then A squared is much, much, much less than B squared. If you take the squares, etc., then this A squared is necessarily neglected. So we have only B squared. It comes out of the root as B, so that the expected force will be approximately capital G, capital M, little m divided by B squared. So it means now this rod, although it has a certain length, some dimension, it is not a point particle. However, if you look at it from a very far away position, just like the electric charges do, remember in the electric field, the same ideas apply. For these very far away positions, to the right or to the left doesn't matter, the rod behaves as a single particle, single point object. Okay? Let me write it here. For very far away positions, the rod behaves as a point particle. As a point object. This is the expected result. Because if you look at the object from a very far away position, you cannot detect whether it's a cube or a sphere or a cylinder or a rod. You can only measure some effect, if it is possible. If you look at it from infinitely far away positions, then you don't even detect the effect of any gravitation or any Coulomb force in the electrical case. However, now you are very far away, you put your little lamp at a very far away position. However, it is not infinitely far, it is just at a distance where that distance is much, much greater than the size of the rod, maybe 100 times, 50 times, etc. Not infinitely many far away, but just a certain large number of times, so that at those positions you cannot distinguish between a rod and a sphere and a cylinder or a disc, etc. You just feel, measure, if possible, just measure the effect of a point particle. So we understand, we obtain this expected result by just putting a very small, taking a very small and taking B outside, so that it is GMM over B squared as expected, but approximately. Now, in the new example, let us hang two identical objects by rows, but let the length of one row be longer than the other one, considerably longer by some distance h. And then, since one of the blocks objects will be nearer the surface than the other one, the gravitational attraction will be slightly different on the two pieces. So let's try to show this difference by some mathematical trick. Two identical objects, each of mass m, are hung by vertical strings whose mass is negligible or whose masses are negligible, but whose lengths differ by h. So the picture is basically the following. Here is the surface, for instance, surface of the Earth, ground. And here is one such block, and here's the other block. They have identical masses m and m, but this distance between them is h. H, where h is of course much less than the radius of the Earth, obviously. No numbers are given, but we will now show the difference. Show that the weights W and W prime, for instance, W is the number, mg sort of, W is the weight, mg is the weight of the upper one, and W prime is that of the lower one. Show that W and W prime. Show that the weights W and W prime have a difference. Of course, this is greater because it is nearer the center of the Earth than the upper piece. So W prime minus W is 8 over 3 pi g rho m h, where rho is the mean density of the Earth. Where rho is the mean density of the Earth. M is the mass of each of them. H is the vertical distance between these two objects. And G is the universal constant of gravitation. Now we consider the effects of pulling by gravity. The forces. So on this one, on this object, of course, there's a certain, let me call it F, which is W. And on the other one, there is a force, which is, let me call W and W prime instead of, W and W prime. W prime is greater because it is negative. Alright. How can we write them? Of course, we will use the gravitational force, G, M, etc. So it is W prime minus W is the following. One is G, mass of the Earth, mass of the object divided by only the radius of the Earth, because from center to center the distance is capital R, which is the radius of the mean radius of the Earth, divided by R squared, minus the same terms appear here, G and M, but divided by the distance between the upper object and the center of the Earth is the radius R plus the additional H. So it is R plus H squared. Now we continue as follows. We can take the constants away. In the result, of course, there's no R. We will use the density, convert the density and the mass using the concept of rho is equal to m over v. Mass per volume is the density. So let's take the constants out. G, M is outside. Inside we have 1 over R squared minus 1 over R plus H squared. But since we have this condition, obviously, because remember that 6,400 kilometers approximately is the radius of the Earth. But this H may be a few kilometers, not more than 10 kilometers, for instance. Very little distance, not negligibly small, but much less than that of the Earth, the radius of the Earth. So we can apply again Taylor's approximation. Since H is much less than R, we can apply Taylor's approximation to the second denominator. But not now, we should arrange it first. How can we apply it, the idea to the second term? Let's see. For instance, we have r plus h squared. So we focus on only the second denominator. How can we rewrite it using this approximation? And assuming that h is much less than r, we know that for the polynomial case, if you have 1 plus or minus x to the power of n, and together with the condition x being the additional part being much less than 1, otherwise it is not possible to apply it. If we have such a condition, then we know that it is 1 plus or minus x to the power of n can be written approximately just keeping the first two terms, because of course that series goes to larger and larger terms, but every other term, every term after these first two gets smaller and smaller, so we can neglect them. But we keep the first two. What are the first two? 1 plus or minus n times x. For instance, remember that if we have 1.1, for example, 1.1 squared, remember, we can write it as 1 plus 0.1 for this 1.1 squared. And applying this idea here, we can write it as approximately 1. Since it is plus, we write plus. Power is n is 2, 2 times 0.1. So it is 1.2. 1 plus 0.2. 1 plus 0.2 is 1.2. And indeed, if you don't make any approximation and just take the square of 1.1, you will get 1.21. So instead of 1.21, which is the exact result, you may approximate it to 1.2, which is a very good approximation. So we can apply this simple method to the case of r plus h squared, because h is much less than that. But we should first of all write it as r 1 plus h over r. This has to be squared, because if you multiply them, r times 1 is r times the second gives us h. So now, this part is in the form of like 1 plus x, this one. So that r squared is independent, we can write it as r squared multiplied by 1 plus, take 2 here, 2h over r. So we can continue from now on. We were here, and we will continue by this simple method. So, w prime minus w. Let me keep the figure on the board, so it will be easier to follow. We were considering these objects, one hung by a rope, the other is hung by a longer rope. This is the ground. And the w and w prime are the values, and this distance between them is, let's say, h. And you approximate the small difference in the weights of these objects because of being at different lengths from the center of the earth. So w prime minus w, we continue from this last sentence, we have gmm over r. Over nothing, multiplied by 1 over r squared minus, now 1 over that term is just 1 over r squared times, this is, if you write it in the numerator, it will be minus 2 r squared, 1 plus h over r to the minus 2, so that we can take 1 over r squared outside, gmm over r squared multiplied by 1 from the first minus 1 from the second, and another 1 minus 2h over r. So if you open the parentheses, you get gmm over r squared multiplied by, if you open 1 minus 1 plus 2h over r, so these ones will cancel. we have just 2h over r. But on the other hand, how can we write this m? Because mass is not given, but rho is given, density is given. On the other hand, the density rho is total mass per total volume. And what is the total volume of a spherical object? 4 over 3 pi r cubed. So it is m over 4 over 3 pi r cubed. 3 comes up. So that here we continue. W prime minus W is G over R squared multiplied by M, but we don't write M, we write it as rho times 4 over 3 pi R cubed. Next we have little m. Next we have 2h over R. So there are some cancellations, such as these R squared, R cancel R cubed. 2 and 4 make it 8, and we get the result. So that W prime minus W turns out to be, yes, approximately 8 over 3 G pi rho M H. By the simple trick of applying Taylor's approximation to a polynomial of this form. 1 plus x plus or minus x to the power of n is just, it can be written as 1 plus or minus nx. In the previous lecture, we have seen the Cavendish experiment to find out what the capital G is, because remember that we had, or they had, they used two balls, two relatively bigger spheres placed fixed on a surface, and using a balance, torsional balance, at which a horizontal very light rod was attached, and then at the ends of the horizontal rod there were two little balls, and they were able to make vertical oscillations around the vertical axis. And using this simple setup, he found out that capital G, which was this constant, numerically is a very small number, as Lord Cavendish, English astronomer, found out capital G was approximately 6.67 times 10 to the minus 11, and the unit is Newton for the force. Meter squared comes here, but divided by kilogram squared. Newton times meter squared per kilogram squared. So it's a very small number indeed, 10 to the minus 11. However, after having found this capital G numerically, they could find several other masses, distances, several pieces of information in the astronomical sense, and then they could find the overall general density of the Earth. And according to this the given data, the density, the average density rho for the Earth is, well, rho is equal to total mass per total volume, as we have said here. But numerically, mass of the Earth is approximately 6 times 10 to the 24 kilograms, approximately. Divided by the volume is, it's assumed to be a sphere, not exactly a perfect sphere, because the diameter from North Pole to South Pole, if you compare the diameter from between the poles and the diameter along the equator, they are not exactly the same, because this part, pole to pole diameter, is 42 kilometers approximately less than the other diameter. So it is a bit a flattened sphere. For most practical purposes, it is not important. However, if you want to have more exact values for some calculations, you should take into account this small difference in the radii. However, let's assume it's a 6,400 kilometers. So 4 over 3 pi and 6,400 kilometers, so multiplied by 3 cube. At the end of this simple calculation, rho turns out to be, and converted to gram per cubic centimeter, although not an SI unit, 5.5 gram per cubic centimeter. It is almost more than 5 times denser than the water. Average mean density of the Earth is more than 5 times larger than that of the water. However, if you go out into the garden, for instance, and take some piece of soil, for example, or from different parts, so that you take an average value, you get something considerably less than this. 5.5 gram per cubic centimeter, a density more than 5 times greater than that of water, is not expected if you take some specimens from around. What does it mean? This is the average value, expected value, and we trust on this result. However, by your everyday measurements, experiments, you cannot get such a high value. So it means that the inner parts near the center are much more denser, much denser than this crust surface part. So that the average value is this much, but since the crust means the relatively outer part of the sphere of the Earth, but since the outermost part of the Earth has a smaller density, it means near the central part, in very inner part, the materials, heavy metals for instance, the materials there have a much greater density than the average value, so that as a result the average turns out to be such a number of 5.5 grams per cubic centimeter. But since the outermost part of the Earth has a smaller density, it means the inner part means central. The inner central part consists of some relatively heavy metals. In liquid form possibly, because the temperature is expected to be a very high value inside the crust. So those high temperature values indicate that it is possibly in the liquid form, but those objects, material there, has much greater density than the average, so that as a result the average turns out to be this much. Now let us consider another example where the object, the spherical system, the sphere, has a variable density, and find the total mass contained and also find the force applied by this system on an external object. Let a spherical object, let's say celestial, like a planet or a star for instance, let a spherical celestial object have a variable density of rho is equal to some rho 0 multiplied by, for instance, 1 minus r over r, where r is the capitalized radius, where capital R is this radius, and rho 0 is a constant. distribution. By a simple picture, for instance. Show the density distribution. B. Find the total mass contained in it. Find the total mass, let's say capital M, contained in it. And C, calculate the gravitational force F acting on an object of mass m at position x, where x is greater than the radius, of course. It is some particle outside the surface. First of all, according to this simple function, of course this function could have been a negative exponential, e to the minus something from the center, for example, e to the minus. Instead of this function, one could have e to the minus, let's say r over r, for instance. This is another possibility, because for smaller little r values, we are near the center, and it is denser. For example, rho is equal to rho 0 times such a negative exponential could also be the possible density distribution. But to make it easier, let's choose this polynomial 1 minus r over r. Part A says, draw a simple picture to show the density variation. So this is the spherical object, and this is the center, for instance. Now forget about it. According to the given function 1 minus r over r times rho 0, near the center where r is 0, we only have rho 0. So the greatest density occurs near the center, just like our Earth, for instance, as I said before. Our Earth consists of some heavier, denser objects, denser material near the center, and as you go to the surface in each direction is not important because it is possibly radially symmetrical. As you go to the surface, you approach the surface part, then that density gets gradually smaller. And this function shows the same behavior. So near the center, let me use some red dots to show the relative density of material. So near the center, we have greatest density. As you go to the surface, where on the surface r becomes just equal to capital R, so there is almost no density, very light material on the surface. However, as you go from center to surface, the density gets gradually less and less. So that near that point we obtain less and less points. So on the surface, very little objects, but near the, for example, if you consider just a sector, circular sector, for instance, along this, there are more concentrated dots near the central part, but they get less and less as you go in this radial direction, according to this function. First of all, this is the general behavior if this is the expected function. Part B is a calculation. Find the total mass. Of course, if it were a uniform density, part B, if it were a uniform density, if the object had uniform density, such as rho, just rho, without any index, for instance, if it had uniform density, of course rho is equal to mass over volume, and mass would be found by just multiplying rho and volume. However, here we don't have a uniform density, instead we have a gradually decreasing density. So we should consider the total spherical volume as composed of spherical shells. But since rho is changing, we should consider the sphere, the spherical object. We should consider the sphere consisting of spherical shells having slightly different density. Consider the sphere consisting of spherical shells having slightly different density. Because of this is a function that depends on the position from the center. So the general idea is the following: m is not equal to simply rho times v, but it is an integral. It is an integral of rho of r multiplied by dv, where dv is the volume of a spherical shell, just like an onion, for instance. An onion. The onion consists of spherical shells. In the atomic models, for instance, in the simple atomic models, the atoms are also supposed to be composed of spherical shells, or those orbitals, for instance, just like the simple onion. There are shells, spherical shells, having a certain radius r, having a certain thickness dr, but the next one has a bit greater radius, again it has a thickness dr, etc. If you add new shells on the previous ones, you get the total shape, total onion, or total atom, or total mass in the sphere. Where dv is the volume of a spherical shell. How do you write the spherical shell's volume? It is a shell like this. So the material is here. And that radius is r, but the thickness is dr. So if you cut this shell, spherical shell, open and cover it on a certain surface, then you get some volume. It has the surface area times some thickness. Surface area of the shape that you lie on the surface has the same surface area as this spherical object. So the surface area, dv, is equal to 4 pi r squared is the surface area of a sphere with a shell or field object. It is 4 pi r squared multiplied by this thickness dr. So we put this dv here, and rho of r is the function, or any other function given in the problem will be substituted here, and the rest is a simple integration. So let's consider this integral now. M is equal to integral. Of course, the limits of variable is from the center r equals 0 to the surface r equals r. Inside the integral we have rho of r. It is given. Rho 0 times 1 minus r over r. Multiplied by the surface area of the shell, which is 4 pi r squared, of course little r, and the thickness dr. Take the constants out. So we take rho 0 times 4 pi. Inside we have an integral for this part, such as r squared dr, and the integral for the other part, r over r times r squared dr. This turns out to be r cubed over 3 between 0 and r. This turns out to be r to the 3, it becomes r to the 4 over 4 from 0 to capital R. So that m is now 4 pi rho 0 multiplied by, we have r cubed over 3 from the first. 4, one of them will cancel when you take substitute. So r to the 3 over 4. So this is 4 minus 3 by 4 times 3. It is 1 over 12. So we have 4 pi rho 0 times r cubed over 12. So these cancel and 3. So that m is equal to, in general, pi rho 0, which is the constant in the density function, times the radius cubed divided by 3. This turns out to be the expected mass according to this density distribution. Now part C, we will find the force. Part C is the following. This is the object, spherical object whose mass we calculated. At a distance x from the center, at a distance x, here we have another object which has mass m, and we will find the force acting on the little object due to this mass. One way is to find the force by just writing this m as the total mass, gmm over r x squared term, or you can use just these spherical shells and add up all the contributions from each spherical shell. One way of finding it is to write it as f is equal to capital G, capital M, pi times rho 0, r cubed over 3 multiplied by little m divided by x squared. So this is the result. Once you obtain the total mass, you could easily use it in the formula. But the other way, in other words, is this way of checking this result. The other way is to add up the contributions of the shells into the force, gravitational force. So for instance, this is the object, total object, big one, and here is the little object, m, and x is the distance, all right, from center to center. However, for example, let's consider just this shell. Let's consider just the red shell. This is a radius r, and it has a thickness dr. Just this shell, having a certain density, rho 0 1 minus r over r, creates a certain force on the little particle. If you add up all these things, you should get the same result. And let us, by the way, check the validity of the result we have found. If they occur as the same result, then we have done it correctly. We should consider the contributions separately as an integration. So for example here, F is the integral of dF. dF is the force just this object applies on this small particle. What is it? Capital D is a constant, and we have seen that every spherical shell or solid object can be considered as if concentrated at its center. So instead of this red particle, this shell, we can consider it as concentrated at the center. So G, inside we have, also x squared can be taken out. X is not a variable, x is the fixed distance. There is no integration over x. G over x squared outside. Inside what do we have? The mass of this particle, which is rho 0, 1 minus r over r multiplied by 4 pi r squared dr. And also small m comes out. So inside this, of course, you get the same result. Take the constants outside, gm rho 0 over x squared. So this 4 pi is taken out. Inside we only have first term r squared dr and second term r to the 4, no square, r to the 3 over r dr. And this term becomes r cubed 0 to r. This term becomes r to the 4 over 4r 0 to r. So we expect to get the same result. Let's check. Gm rho 0 4 pi divided by x squared multiplied by r. This is, remember, r cubed over 3. So that 1 over 3 minus 1 over 4, it is 1 over 12. So we have r cubed over 12. Let's see now the cancellations. Do we get the same result? Let's see. And these become 3. So here we have g m rho 0 pi r cubed over x squared. Of course, the force would be the right hand side. Let's compare the results. This one with that one. Do we have the same term? Yes, we do. Gm rho 0 pi, Gm rho 0 pi, r cubed over 3x squared. 3 is also here. So we obtain the same result, which means that we found the mass of varying density correctly. And secondly, the idea that every spherical shell, the mass of every spherical shell can be considered to be concentrated at the center in a little volume is also correct, so that we obtain the same result by two approaches. Now let's see Kepler's laws, which are quite important in astronomical topics, declared in the 17th century. So basically there are 3 such laws stated by Johannes Kepler based on the large data collected by Tycho Brahe and another astronomer. So let's now see briefly what these laws state. For the solar system, for instance, and in several other systems in astronomy, a star, of course, in space there are billions of stars having different sizes, different masses, with a wide range. And the stars, some of them have planets around. So a general system, such as our solar system, the central part is the sun, is the star. In our case, it is the sun. And around the center, this is not a perfect center because those orbits are not circular, they are rather elliptical. In our system, they are not just like a perfect ellipse, maybe quite like a circle. However, the general form of the orbits is ellipse. How do you state those 3 laws in words? They can be said like this: Kepler's laws. For instance, 1, the planets in our solar system, in the solar system follow or move in orbits, move in elliptical orbits, move in elliptical orbits. sun, which is the reason for those planets to revolve in elliptical orbits, the sun is at one of the foci. At one of the foci. Foci is the plural of focus. So, for instance, this is a general form of an ellipse. X-axis, y-axis, and there are two important parameters: major axis, minor axis values. Say this part is A, and that part is B. So the general formula for an ellipse is x squared over a squared plus y squared over b squared is equal to 1. So this is the general expression that defines an ellipse. Of course, if A and B are the same, for instance, if A and B are the same, or were the same, it would be, if, let's check this formula, if x and y, if A and B are the same, A is equal to B, which means this major axis and the minor axis are of equal length, there is no difference, therefore they can be called the radius r. So each of them is equal to r. In that case, of course, we would have x squared plus y squared over the same value, r squared equals 1, and then we can take r squared here. So this is the equation of a circle. So a circle is obtained by setting the two major axis and minor axis values equal. So this is the general form. And there are two foci. One focus is here, let's say, one focus, the other one is there. It's an exaggerated way, of course. But for example, here is the sun. The sun is at one of the foci, and this is an elliptical orbit. The orbit of one of the, any one of the planets, for instance. Mercury, Venus, Mars, Earth, etc., Jupiter, Uranus, Saturn, whatever. And there are such ellipses. And each planet revolves in one of the ellipses, but it is the sun, which has almost 99% of the total solar system, so the mass of the solar system. So it is, the basic part is the sun, of course. So the first law simply says that each planet in the solar system moves in an orbit, but elliptical orbit. Second one is, let's focus on one of these planets. Second law briefly says the following. Let me consider just one circle, one ellipse, and for simplicity, let's say this is the position of the sun, and for example, a planet at a certain moment is, let's say, at position A. And let's join these two so that we have the radius vector. For instance, during a certain time, let's say that time is delta t, maybe 1 month in a year, that planet arrives at the new position B, for instance. On the other hand, or at a different, in a different part of the year, for example, this may be the movement from point C to point D. So if you compare them, for instance, if these time intervals are the same, so this time is also delta t, maybe 1 month to come from A to B, and 1 month come from C to D, for example. If this is the case, if this is the case for the yearly journey, then the areas swept by these radius vector will be the same. So the area or the areas swept by the radius vector. This is called a radius vector that joins the sun with any planet. The area swept by the radius vector in equal time intervals are the same or are equal. So this is the second of the Kepler's laws. And the third one is on the periods and the radius vector. So the third one is the following. Now in the third case, let's consider only two masses. One, for instance, let's say, let me draw the object like this. So this is capital M, for instance. And the other one is here. Let me call it little m. So from the picture it is understood that capital M is a bigger object with respect to the other one. Yeah, if they have such an interaction, gravitational attraction, they both are revolving. But they are revolving around the center of mass of the system. But if you join the center of these, the centers of these objects, for instance, like this, so this is the line joining them, the general overall center of mass maybe corresponds to, let's say, somewhere here. This is the center of mass, which means that this object makes a rotation around the center of mass with such a radius, let's say capital R, but this one does the rotation, completes it the other way with this radius. However, in the case of the solar system, the mass of the sun is so much greater than all the other planets' masses, so that the center of mass of the whole system almost corresponds with the somewhere inside the sun. So the distance, the capital R for the sun in the solar system is negligible with respect to the other radii. So let me draw this picture in a bigger way. For example, in general, this is the motion of the bigger object. Let me just take three moments into account. Okay, and this is the general center of mass. For instance, this is the first, that's the second, and that's the third moment. These are the, this is the order of rotation for the bigger object. These are the three instances. On the other hand, when the object, bigger object, is at position 1, somewhere here, let's say, the small one is like this. But when the bigger object moves to the position 2, for instance, this is the new position of this one. And when it is in 3, let's say, it is somewhere. So on the one hand, the bigger object follows a smaller circle having radius r, but on the other hand, smaller object is at a distance of r. However, let me repeat, in the case of the solar system, since the mass of the sun is much greater than the mass of even the Jupiter, which is the greatest of all the planets, so that the center of mass of this mutual rotation corresponds to a position inside the sun. It is even not outside it. So that the force of interaction, capital G, mass of the first, mass of the second, divided by, this time we should take into account the sum of these distances, r plus r. And we write r plus r squared. On the other hand, what is the right hand side? It is the centripetal force, acceleration on the right hand side. We talk about a little object, it has mass m. Either we write it as v squared over r, or we write it as omega squared times r. Omega, angular velocity of this rotation, times the radius r. But in this, if for instance, m is much greater than the other mass, which means that r plus r can be taken as r. Because in this case, r is much greater than capital R, so this capital R is neglected. Therefore, we have, instead of this r plus r, we simply have just a little r. And then take this r here. So that this expression now becomes, after the cancellation of little m, mass of the planet in this case. So we have capital G, capital M, on the one hand, is equal to omega squared times the r, this is r squared, so this becomes r cubed. Omega squared r cubed. But we also can write this expression in terms of the periods. And how do we get period into play? We know that omega is equal to 2 pi over t. Because omega is, remember, 2 pi nu, and nu is 1 over t, so omega is 2 pi over t can be written. So instead of this omega squared, we can write it as 2 pi over the period of this planet squared. Next, we have G times M. On the right, we have, if you take the squares, 4 pi squared over the period squared times radius cubed. If you take it to the other side, for instance, t squared there, so that t squared is equal to some constants which are not important, of course 4 pi squared over g and 4 pi squared over gm multiplied by r cubed. So in other words, we have t squared equals something times r cubed. We can apply this idea to a second planet as well. Because anyway, all the planets have masses considerably less than that of the Sun. So that for the planet 1, we have t1 squared equals r1 cubed. For the other planet, any other one, for instance, we have t2 squared over the same terms, not important. We are 4 pi squared over gm, but it is not important in this analysis. So on the right hand side we have r2 cubed. So that if you divide them side by side, these constants cancel. So t1 over t2 squared is proportional to, or in this case it is equal to, r1 over r2 cubed. So this is the third law. So ratio of the two periods divided by squared will be equal to ratio of the two radii squared. If you compare any two planets, Jupiter and the Earth for instance, if you take the 1 year, for instance, period of 1 year for that planet, T Jupiter for instance, T Jupiter by T Earth squared can be written as the radius vector followed by Jupiter divided by radius by Earth, for example, cubed can be written, or for any other pair of planets, for instance, can be written. So this is the other law. So Kepler, in those years of 17th century, stated these three laws and made several observations, of course. Some other he made several contributions to the topic of this astrophysics. Of course, in those years there was no physics, no astrophysics. However, the astronomy was the development of astronomy. Some part goes to Johannes Kepler. Now let's consider another important topic, which is the potential energy, gravitational potential energy. We have seen potential energy in the previous chapters, but now we have gravitational potential energy. When we hear the words potential energy, we understand we immediately remember the formula U is equal to mgh, for instance. The first thing is potential energy is mass times gravitational acceleration times the height with respect to a certain reference frame. For example, if we have a block on the ground and we take it to a certain height in a building and put this object here by taking it up, lifting it to a height h, for instance, then when this object is brought to a higher position of this much, then it has a certain potential energy of mgh. It doesn't use it now, however, it has the possibility of using it. If you simply tip this object from the window, for instance, it falls down, and maybe by just hitting this ground, if just it hits the ground and it can make this nail penetrate into the ground, for instance. Or if there's a certain whale here, for example, by just falling on the wheel, it can cause the wheel to rotate so that potential energy can be converted to kinetic energy, for example. However, now we will try to see the gravitational potential energy. What is the difference between them? In such topics, we have taken the event to occur near the ground. What does it mean? H, for instance, was much less than the radius of the Earth. So that we took mg, the weight of the object, as a constant. So these heights, several meters, maybe several hundred meters at most, this height or any other typical height in those chapters was on the order of some meters, hundreds of meters at most, or tens of meters. So those heights were negligible with respect to the radius of the Earth, so that this is the Earth, that's the radius of the Earth, and if you are somewhere here, this increase in the radius was negligible, so that mg was a constant. And that potential energy, in fact, was found by, they worked out f dot, let's say dy. Y is the vertical height. Let's say this is the y-axis. This is the y-axis, okay? If you take this object, if you carry it to a certain height, then you do work against gravity, because it is, you get some difficulty in moving this object to a certain height by doing so. Therefore, and f was mg, so that mg, which was a constant, it can be taken out of the integral, and this dy turns out to be y. So mgy limits from 0 to certain height h, so that potential energy was the work done by your force would be mass times gravitational acceleration and g times h. However, now in this section of this chapter, we are interested in some changes in the height, and those heights, h values, are not negligibly small, so that mg is not a constant. G changes, for instance. Therefore, this integral now is modified. Instead of this constant mg, we take the force gmm over r squared. So now the values of these heights h are not negligible with respect to the radius of the Earth, or radius of any other planet. So now the values of h are not negligible with respect to the radii of the planets, for instance, or those celestial bodies. So that instead of f is equal to mg, f is not equal to now mg, but f can be written as gmm over the distance squared. So f depends on the distance, which does change, not constant as in the previous cases. So that potential energy can be written as gmm over r squared multiplied by dr, and therefore it is, we take gmm outside, but minus dr over r squared turns out to be minus 1 over r, minus 1 over r. And these limits from 0 to infinity to a certain r, from infinity to a certain r, because we have an object here, let's say object m1 having mass m1. Now you, from infinity far away positions, you bring in a second object nearby, so that you do some work. Therefore, the system gains a certain potential. What is that potential? Potential energy. This U turns out to be minus G M1, M2 divided by R if these two objects, M1 and M2 are the masses, are at a distance of R from center to center. So this system, consisting of just these two bodies, has a certain gravitational potential energy. But if you change this configuration to a new configuration, for example, let's say the initial value, final value. Initial case is we have first object and second object, mass M1, mass M2, at a distance of R1. Now, by some means, for example, we try to take them a little further apart. Then, for instance, in the final case, we have the M1 here, same object, same position, M1, but now move the second one to a greater distance, let's say to a distance R2 now. R2. Okay? So this is the new separation. Therefore, they have different potential energies, gravitational potential energies. First one was U1 is equal to G M1 M2 over R1. Second one is U2 G negative 1. Of course, don't forget the negative sign, because here a negative sign is necessary, because otherwise this system cannot be stable. It is impossible for a system of particles to stay together as a stable system with a positive potential energy. Necessarily that system should have a negative potential energy. In some cases, we generally want to get positive values. Negative values are not very very good things, maybe. But in these cases, negative values are better for stability. So they have negative signs here, G, M1, M2 divided by new separation, R2. Now let's consider another example based on these ideas. In the simple case, let's have more than two objects. If we have more than two objects, we find the gravitational potential separately, 2 by 2. Because we find them independently for each case. If there are more than two objects in a system, such as, for instance, M1, M2, M3. For instance, for simplicity, let's choose the xy plane in free space and put those objects at those positions. For example, M1, M2, and M3 are the masses of these objects, and A and B are the distances between them. So for such a system, the potential energy is simply found by the compact formula of minus G and a summation. In the summation, we have Mij divided by R sub ij, which means you simply multiply two masses, 2 by 2, then divide this product by the distance between that ith and that jth particle. But this is simply, for this case, for example, now we take the negative g outside, let me write it here. Minus g is taken out, and after that we have, start with M1. M1, now next one is M2. Since potential energy is a scalar quantity, we don't have any directions, sine theta, cos theta, etc. So M1, M2 divided by the distance between them, A. There is no square like before. Plus the other pair is M1, M3. M1, M3 divided by B. And finally, M1 is finished, so we have the other pair, M2, M3. M2, M3 divided by this distance, which is the square root of A squared plus B squared. That's it. There's no more need to find the calculations. This is enough. Next, let's have another example, but before that let's consider the case of infinitely far away masses. For example, if you have an object here, M1, and an object there, M2, R is approximately infinitely far away, then this system has almost no potential energy, obviously, because of the denominator of infinity. So for this system only, then U will be minus G M1, M2, but divided by such a long distance that the fraction is almost nothing. So this is almost 0. Now let's have a problem on this. Two objects having masses capital M and little m. are initially infinitely far apart and at rest. But after a moment, they try to approach each other. They start, after a moment, after a while, they start to approach each other. Part A, find the relative velocity of one with respect to the other when their separation is r. Find the relative velocity of one, anyone, of one of them with respect to the other when the separation between them is r. And B, find this relative velocity when they collide with each other. Part B, find this V relative when they collide with each other. Now the physical things here are the conservation of energy and conservation of momentum. Part A. There is conservation of energy and conservation of momentum, linear momentum in this problem. Why? Because there is no dissipative force acting on the system, so the total energy should be conserved, and also there is no external force acting on this couple, this pair of objects from outside, so that the momentum should be conserved, algebraically of course. Initially, energy is zero, no kinetic, no potential. Momentum is zero because there is no motion. But at a later time, at any later time, again the algebraic sum of the energy and the momentum should add up to zero. So initially, let's say capital M, little m. So capital M is here, little m is there. They are infinitely far away. So what is the energy of this system? Energy initial at the beginning where they are when they are infinitely far away. This is just energy, kinetic energy, potential. So kinetic energy plus potential energy. Kinetic initial, potential initial. What is kinetic initial? There is no velocity, so that it is zero. What is potential initial? Minus, according to this formula, we can say that it is negative g mm over infinitely far away. So this is also zero. Totally, there is no initial energy of the system. What about the initial momentum? P initial. 0 plus 0, so P initial is also 0. What about their energy and momentum when they are at a distance of r? Let me call it finally. It is not the final position. After this substitution, we get rid of the capital V and instead write the right hand side. So that this upper equation, which is initially 0, can be written as what? 1/2, take it outside. Capital M, capital V squared, little m, little v squared is equal to G mm over the r. But this v is now replaced by the right hand side so that we have 1/2 capital M, capital V squared. So we have little m squared by capital M squared, little v squared, and the second term, and G mm over r. Well, mv squared is the common term, so we can take it out and we can cancel one of these capital M's. So we have, let's take 1m, 1v squared divided by 2. Inside, what do we have remaining? This little m over capital M plus 1. So it is the right hand side gmm over r. And that becomes little m, little m's cancel, by the way. These little m's cancel. So we have only v squared, little v squared. So we have capital M plus m by capital M is just g capital M over r. And then this v squared is just g m squared over m plus m times the distance between them r. But we will find relative velocity. Relative means it is the sum of the two velocities. Because if we are going at 50 kilometers per hour and another car coming against us at 60 kilometers per hour, the relative velocity is just 60 plus 50, which is 110. Since we have no relativistic speeds, these velocities are much less than the speed of light, so we can simply add them without any extra formula. So V is the root of the right hand side. We can take m outside, it's a square. So inside the root, we have capital G over m plus m times r. But V relative, we are still in part A, V relative is capital V plus little v. It is the sum of the two absolute values. Because anyway, since they have opposite stances, we have to add them up to find the relative value. Capital V was just this term, so we have little m over m times little v plus little v. So that V relative is just, take V here, we have little m over capital M plus 1, little v m plus m over m, and that V is now brought here, so we get the final result. Therefore, V relative will be m plus m over capital M multiplied by capital M and the root of g over the denominator. So these m's will cancel. If you take the square of this and put it inside the root, we will get the final result. V relative will be root capital G multiplied by m plus m after the cancellation divided by the distance between them. That momentarily, at that moment, the distance was r. Part B, now assume that they hit each other after continuing in this same axis after a while. then if they collide with each other, then R will be simply sum of their radii, for instance. Therefore, V relative will be root G M plus M over R plus R. When we consider the potential energy created by some force, attractive force on an object that comes in from infinity, the important point, this is also valid for the electrical cases as well. But for instance, if this is the attractive center and here the object is, now let me draw some possibilities. For example, in all these directions, this is the force acting towards the attractive center. And we have some object, let's say here. When it is coming towards the attracting center, it follows, for example, such a curve, such a path, different path. And for instance, it is coming along this direction, and then going along the other one, then for example, follows such a path. If it follows such a path, then the only parts which are important are the red parts. These are the radial parts. And the sum of them is the general distance r. During the dotted part, during these curves along the tangential curve, because these are tangent, then it is not important to go along the tangent in such a case because the directions are perpendicular. So for example, when the object is here for a moment and then it goes along a tangent, in that case the force is making an angle of 90 degrees with the f dot dr, remember? F dot dr will be 0 for along the tangents, these black curves, f dot dr is 0. So the important part is the sum of the work done, the energy. Energy is found only by the sum of these different parts. If you add up only these radial parts, so it is the sum of radial parts that make up the total potential energy or work done. Now let's finally consider the concept of escape velocity, which is also important in such phenomena. The escape velocity is briefly the following concept. For example, on the Earth, if you throw something into the air, perpendicularly upward or in a projectile manner, so this is the object, for instance, if you throw it into the air, it goes to a certain height and, of course, falls back with some initial velocity v1. If you throw it with a greater initial velocity v2, it goes to a greater height, however, it falls back, v2. If you throw with still a greater initial velocity v3, although v1, v2, v3, for instance, maybe the corresponding heights change as you increase the object with a greater initial velocity, the height it can reach can increase, obviously. So h1, h2, h3, and these heights are like these maximum heights from the ground. However, in all such cases, it is necessarily expected that the object, once thrown up, anyway, sooner or later comes back and falls down because of the gravitational pull of the Earth. Is it possible to throw an object upward, for instance, maybe directly, maybe at a certain angle, such that it doesn't come back and goes to infinitely far away position? Is it possible? If you throw the object with sufficient initial velocity, it is indeed possible. But how do you find that initial sufficient velocity of throwing the object? If we throw an object with sufficient initial velocity, what do we mean by sufficient? We will see. If with sufficient initial velocity, let me call it v escaped, so that the object escapes from the Earth, v escaped, then it will never come back. It will never come back. Now let's try to find this minimum necessary velocity by some energy considerations. If you send an object into free space with, for example, this is the Earth. This is our Earth, and we throw something into the air and it falls back. If you throw something with a greater velocity, it will come back. But if you throw an object such that the gravitational pull is not enough to keep it near the Earth, it will go far away. But the energy necessary for this can be found by the energy conservation. Let's consider two positions. One just on the surface at the radius r from the center, and the other is infinitely far away. So this distance is r is equal to infinity. From the energy conservation between these two things, but kinetic and potential should be taken as the sum. By considering the energy conservation, we can find the escape. By the conservation of energy, E1 is equal to E2. In other words, E at the position R is equal to E at the position at infinity. What is the total energy here? For instance, UR plus KR, U infinity plus K infinity. On the surface of the Earth, an object having mass little m, now the mass of the Earth is capital M. What is the potential energy that we have learned? Gravitational potential energy is negative capital G, capital M, little m divided by just the radius of the Earth, plus the kinetic energy which we want to find. It is 1/2 m, little m of course, mass of the flowing object, flying object, mass times v escape squared, which is the unknown we want to find. On the right hand side, the potential energy at infinity, so we have to write minus g capital M little m divided by infinitely great radius, and plus additional kinetic energy if it has any at infinity. Since we want to find the minimum value for the purpose of escaping, then there is no need to have any additional kinetic energy. We can take it as 0 for V escape minimum. Of course, if you throw the object with greater energy than the necessary minimum value of escape velocity. Of course, even at very far away positions, the object may have still some remaining velocity, some remaining kinetic energy. Now, neglect all such possibilities. Take this additional kinetic energy as zero so that we can find the minimum value of escape velocity. What do we have? This is also zero because the denominator is very, very large. And from this equation, you can easily get the necessary value. For instance, here, for the Earth, now we take this negative term to the right-hand side so that we have 1/2 mv squared. We have 1/2 little m v escape squared is taken to the other side, capital G, capital M, little m, divided by the radius of the Earth. And there is only one cancellation, such that the m cancels. So V escape is simply the square root of 2g m over r. So this is the value which is the necessary minimum velocity on the Earth to throw an object into free space such that it will never come back. Let's find the numerical value for the Earth, for instance, or for the Moon. The numerical value for the Earth. For instance, if you go out to the garden and send an object, a rocket for instance, to free space, with this much velocity, it is expected not to come back. And let's find that minimum value. For instance, here we know that g is equal to 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Mass of the Earth is simply approximately 6 times 10 to the 24 kilograms. And the radius of the Earth is approximately 6,400 kilometers. If you convert it to meters, it will be 10 to the 3 from this, and 10 to the 3 from the conversion from kilometer to meter, so that it is 6.4 times 10 to the 6 meters. So if you put them in the equation we obtained, V escape is simply root twice 6.6 for the g, 10 to the minus 11, times the mass of the Earth, which is again another 6, 10 to the 24, divided by another 6.4 times 10 to the 6. So there are some cancellations. For example, these 6's may cancel approximately. So V escape is nearly root 6 times 2 is 12 times 10 to the what? Minus 11 from the first, plus 24 minus 6, so that it will be 10 to the 7. It is around 1.2 times 10 to the 8 if you take it here, take the decimal point here. So the result is approximately, V escape is 1.1 times 10 to the 4. 1.1 times 10 to the 4. In other words, V escape is roughly 11 kilometers per second. So it's a very high velocity. If you manage by some technological way, if you manage to throw an object up to the 11th kilometer in the first second, then that object will never come back, for sure, because it has the sufficient necessary velocity at the beginning of the motion, and it will never come back. This velocity, if you put the correct data, because the escape velocity depends only on the mass of the planet, for instance, from which the object will be thrown, and the radius of that planet. For example, we can find the escape for the Jupiter, for the Moon, even for the Sun, if it is possible, for example, for Mars, etc. For example, for the Moon, let me give the final piece of information. For the Moon, this escape velocity is not, of course, as large as this much. because the moon has the mass of almost 1% of the mass of the Earth. 1.12% of the mass of the Earth. So that instead of this value, 6 times 10 to the 24, it will be approximately 10 to the 22, 1%. And the radius is not as large as this much, but it is 1,750 kilometers, so this will be almost 1/3 of this. Therefore, V escape, G is the same, 2 is the same, but V escape will be smaller, because this is just 1/3. However, in the numerator we have 1%. Therefore, the corresponding escape velocity is around several hundred meters per second. And most gases, for instance, gaseous elements, can easily escape even at the temperature of almost 3 kelvins in free space. Because in free space, only on the moon, the temperature is around a few kelvins, just above the absolute zero, as we know. However, even at those low temperatures, the gases have enough, the particles, the molecules of those gases have enough energy, enough velocity to escape the atmosphere of the moon, so that there's no atmosphere for the moon, for instance. Why is there no gas as an atmosphere on the moon? It is because of this relatively low value of the escape velocity. Because anyway, those particles have sufficient energy at the beginning, so that there's no reason for them to stay just around the surface of the moon. They can easily escape. However, for the Earth, for example, this is the necessary velocity they should have if they want to escape. And 11 kilometers per second is a sufficiently high value. So those particles, as we know, have some hundreds of meters per second. Maybe it was 1 kilometer per second. However, this is more than 10 times that. So of course, some gases, several gases, do remain in the atmosphere around the Earth. But for instance, for the moon and for other some planets, for instance, because of the relatively lower value of the escape velocity, those gases, particles, molecules of those gases, have at the beginning, for instance, enough sufficient values of velocity so that it is possible for them to escape to infinitely far away positions.